Number 4, we're given a reaction, and they say the reaction proceeds spontaneously. That's pretty important. So right now I'm going to make a note to myself that delta G is negative, because that might be important a little bit later on. Predict the sign of the entropy change delta S for the reaction. Well, we remember that entropy has to do with the amount of order. And you notice there are a lot of gases on this side and no gases on that side. And so that's going to be sort of an organization. The other thing is we have 3 moles of gases going to none, or we have 3 moles of gases going to 2 moles of liquids. Either way, it all indicates that the delta S is going to be negative, as in things are going to be becoming more orderly. So my answer is the sign of delta S will be negative, making sure I answer the question first, because there is an increase in order during the reaction. And then of course I need to have the evidence for that. And the evidence is that there are fewer moles of products than reactants. Now you notice I didn't mention the gas thing because I felt like this was fairly conclusive. But you certainly could say 3 moles of gases become 0 moles of gases on this side. I think either way at this point is fine. Part B, how would the value of delta S for the reaction change if the product of the reaction was water that's a gas? And so we got to remember we've already predicted that the value of delta S would be negative. So I guess the question is, would it be more or less negative if this had been a gas on this side? And it's still going to be negative because then we have 3 moles of gas going to 2 moles of gas. But I don't think it's going to be more negative. So my answer is here. The value of delta S would become more positive. A gas contains more vibrational movement, making water gas have a higher entropy than H2O liquid. So look up here, I've drawn a diagram to kind of explain this idea. So the entropy of the starting materials we think is higher because there are more gases and they have more random movements. The liquid is lower in entropy, and that's why we're getting this negative delta S. So we normally use these kind of diagrams to represent delta H, but we certainly can do it with delta S as well. And since we're talking about, well, what if we were making gas, we think gas has more vibrational movement as well, so its entropy will be higher. And if you look it up in Appendix C, you'll find out that that's true. So the gas version of it will be higher in entropy. So when you do the exact same sort of diagram with the H2O gas, you'll notice that the difference, the delta S here, is going to be smaller. It's still going to be negative probably, but it's going to be smaller. And that's what we're explaining here. I think the diagram is helpful, so it might be something to keep. And so this is sort of summarizes the diagram. This will make the delta S less negative when H2O gas is produced. Now there are lots of other ways to explain this. You don't have to have this diagram, and I worry a little bit by drawing it like this that we're going to confuse delta S with delta H. We're not giving off heat here. It's a change in disorder. So, if you understand the original idea that gases have lots of random movements, which causes a high degree of entropy, well, then the liquid is going to have much lower entropy than the gas. The gas will have much higher entropy. This is just a nice way to kind of show that if the gas has a higher entropy, the difference between it and the starting materials is less. So if they're both negative, this one's going to be a little bit less negative. The answer to C we talked about at the beginning. What is the sign of delta G? Explain. Delta G is negative. And the reason? Because they said the reaction was spontaneous up here. If it occurs naturally, then it must have delta G as negative. You should put a period on the end of your sentence, though. In part D, they want to know what the sign of delta H is. Well, we learned what delta S was up at the top, and we learned what delta G was. And so the way we relate all of them is using the Gibbs-Helmholtz equation. So let's think our way through it. If delta G was negative, which it was at this temperature, you remember delta G can change, but it's been at 298 the whole time. And we knew that delta S was negative. And this is an unfavorable delta S. It in and of itself is not going to make the reaction spontaneous, yet the reaction is spontaneous, or thermodynamically favorable, as they like to say this year. So what does delta H have to be? Well, is it possible for delta H to be unfavorable? And the answer, of course, is no, that can't happen. The reason is because we can't have both terms be unfavorable but then get a spontaneous delta G. It must be favorable. And as you remember, favorable is exothermic, giving off heat for delta H. So it must be exothermic. And what's the sign of an exothermic reaction? Well, negative. So we know the sign based on that principle. So here's my answer. Delta H must be negative. Since the entropy delta S is negative and unfavorable, the delta H must be negative for the reaction to have a negative spontaneous delta G. Easy enough, we're done.